Security is a funny, elusive thing. You will rarely hear a security professional describe something as secure. You will hear that more or less an alternative. But security depends on the context. We will talk about ways to make your Kubernetes cluster more secure. We will also talk about how you can configure your Kubernetes to improve security. I will also talk about some precautions you can take to limit the likelihood of a breach by an attacker and to limit the likelihood of that breach, which eventually results in data loss. Hi everyone, this is Kavya from Edureka. Welcome to today's session on security. Before we move ahead, I'd like to address the agenda. Firstly, we will talk about some of the challenges that Kubernetes can face because of security. Then we'll move ahead and talk about some of the security principles. And then finally, we'll address the main topic of today's session and discuss Kubernetes security practices. We'll conclude this session with a case study. I hope the agenda is very clear. So without much ado, let's get started. Kubernetes security challenges. Now, you can use plenty of non-Kubernetes specific security tools and approaches. You can layer traditional network firewalls and intrusion detection systems. But it is a possibility for you to have an air-gapped deployment. And wherever humans interact with your system, they may constitute a risk to security, either maliciously or just due to human error. Now, there are various ways that an attacker could attempt to compromise your Kubernetes cluster and the applications running on it. So now the diagram that you can see on the screen has some vulnerabilities or security problems that can occur in your Kubernetes cluster. One of them is easy access to the etcd API. Also, the breachers can access via Kubernetes API or proxies. They can intercept or modify or inject control plane traffic. They can also access the machine or VMs as a whole. They can access via kubelet API and exploit vulnerability in application code. All these vulnerabilities and security risks that I just mentioned can cause a great deal of data loss or information from your organization, and this can eventually cause a huge loss. So to avoid all of these risks that Kubernetes clusters fail, let's move ahead and talk about some of the security principles. The first one is defense in depth. Now picture a medieval castle under siege. Okay, it has strong high walls to keep undesirables or their enemies out, and the wall is surrounded by a moat with access via a drawbridge that is lowered only occasionally to let people in and out. The castle obviously has thick doors and bars across all windows. Archers patrol the castle walls, ready to fire at any attacker. Now the castle has several layers of defense. Attackers who can swim might be prepared to cross the moat, but then they have the walls to scale and the likelihood of being picked off by an archer. It might be possible to compromise any given layer in the defensive structure, but by having several layers, it is really hard for an attacker to successfully enter the castle. This is the same ideology that we will have to apply in Kubernetes. It is preferable to have several layers of defense against attacks on your Kubernetes cluster. Relying on a single defensive measure, attackers might find their way around it. The second Kubernetes security principle is the principle of least privilege that tells us to restrict access so that different components can access only the information and resources they really need to cooperate correctly. Now, in the event of a component being compromised, an attacker can reach only the subset of information and resources available to that component. This limits the blast radius of the attack. Now let's take an example of an e-commerce store. Okay, let's assume it is built using a microservice architecture with functionality broken into several small discrete components. Now, even if the product and user information is held in the same database, different microservices might each be granted access to only the appropriate parts of that database. A product search microservice needs read-only access to the product tables, but nothing more. Now, if the microservice somehow gets compromised or simply has a bug, the broken service cannot override production because it has only read access, or even extract user information because it has no access to that data at all. Applying the principle of least privilege means that we make it more difficult for an attacker to cause damage. The same principle can apply to humans too. Now, in some organizations, sharing production credentials with all staff may make sense. In others, it's critical that only a small set of people have access, especially if that access is too sensitive information such as medical or financial records. The third Kubernetes security principle is limiting the attacks. Now, the attack surface is the set of all possible ways a system can be attacked. The more complex the system, the bigger the attack surface, and therefore the more likely it is that an attacker will find a way in. Consider the castle metaphor again that we discussed previously. The longer the length of the castle walls, the more archers we would need to patrol them efficiently. A circular castle will be most efficient from this point of view. A complicated shape with lots of nooks and crannies would need more archers for the same interior volume. Now, in software, the fundamental way to reduce the attack surface is to minimize the amount of code. So the greater the complexity, the more likely the latent vulnerabilities exist, even in well-tested code. With this, we move on to the main part of today's session, that is, we will be discussing the Kubernetes security practices. In the early days of Kubernetes, the default settings left the control plane insecure in important ways. The situation is further complicated by the fact that different installation tools may configure your deployment in different ways. The default settings now have been improving from a security point of view, but it is what configuration you're using. Now, we're just going to talk about the configuration settings that are important to get right for the Kubernetes control plane components, and then we'll talk about some tools that can be used to verify the deployed configuration. So the first one is the API server. As its name suggests, the main function of the Kubernetes API server is to offer a REST API for controlling Kubernetes. This is powerful. A user who has full permissions on this API has the equivalent of root access on every machine in the cluster. The command line tool kubectl is a client for this API, making requests of the API server to manage resources and workloads. Anyone who has write access to this Kubernetes API can control the cluster in the same way. By default, the API server will listen on what is rightfully called the insecure port, that is port 8080. Any request to this port bypass authentication and authorization checks. Now, if you leave this port open by mistake, anyone who gains your master is running on has full control over your entire cluster. So it is important to close the insecure port by setting the API server insecure port flag to 0 and ensuring that the insecure bind address is not set. The next way to secure your cluster is by using kubelet. The kubelet is the agent on each node that is responsible for interacting with the container runtime to launch pods and report node and pod status and metrics. Now, each kubelet in the cluster also operates an API through which other components ask it to do things like starting and stopping pods. If unauthorized users can access the API on any node to execute code in the cluster, it is possible to gain control of the entire cluster. Fortunately, layers of defense are now available in Kubernetes that make it easy to prevent this kind of attack. Firstly, you can limit the API access to authenticated requests, that is, anonymous requests are ignored. And secondly, you can leverage access control to stop unauthorized actions from being performed. More specifically, there are some configuration options to lock down the kubelets and help minimize the attack surface. That is, you can disable anonymous access with the anonymous authentication is equal to false, or ensure that requests are authorized by setting authorization mode to something other than always allow. You can also limit the permissions of kubelets by including node restriction. Finally, you can set read-only 0 to turn off the read-only port. The next way to secure the cluster is by running etcd carefully. Kubernetes stores configuration and state information in a distributed key value store called etcd. Anyone who can write to etcd can effectively control your Kubernetes cluster. Even just reading the contents of etcd could easily provide helpful hints to a would-be attacker. Therefore, you need to ensure that only authenticated access is permitted. The Kubernetes dashboard has historically been used by attackers to gain control of Kubernetes clusters. It is a powerful tool, and in older versions of Kubernetes, the default settings made it easy to abuse. For example, the dashboard sometimes has full admin privileges by default. You might want to take several steps to ensure that your Kubernetes dashboard is not an easy entry point for attackers, including but not limited to the following. That is to allow only authenticated access, use RBAC, which we will talk about later on in the session. Also make sure the dashboard service account has limited access, and definitely do not expose your dashboard to the public internet. Finally, you can secure your cluster by validating the configuration. Now, once you have set up your Kubernetes cluster, there are two main options for validating whether it is configured safely. These options are configuration testing, where tests validate the deployment against a recommended set of testings, and penetration testing, where tests explore the cluster from the perspective of an attacker. Now that we've discussed the first part of Kubernetes security practices, let's move on to the second way, authentication. Now, if you've been using public cloud offerings such as AWS, Microsoft Azure, or Google Cloud Platform, you might have come across the term identity and access management, which allows you to define access for users and services. Now, all components such as a kubelet running on a node, as well as users issuing kubectl commands, need to communicate with the API server. To process the request, the API server first has to verify who is using the request. The server has to establish the identity of the caller, or in other words, to authenticate the caller. So we'll discuss how authentication in Kubernetes works and the options you have in hand as a cluster operator. The first one is identity. Now, for the API server to authenticate a request, the request issuer needs to possess an identity. At the time of writing, Kubernetes doesn't have a first-class notion of a human user, but rather assumes that users are managed outside Kubernetes via a directory service, such as a lightweight directory access protocol or a single sign-on login standards like security assertion or Kerberos. This is the standard approach in production, but if you are not using such a system, other authentication strategies are available. User accounts are considered cluster-wide, so make sure that the usernames are unique across namespaces. It's obviously not just humans who interact with Kubernetes. We often want a programmatic way for applications to communicate with the Kubernetes API, for example, to query, create, or update resources such as pods, services, or deployments. To that end, Kubernetes has a top-level resource to represent the identity of an application, the service account. Now, a service account is a namespace resource that you can use if your app communicates with the API server. Here, many business applications don't really need to manipulate Kubernetes resources in this way, so they can have the service account with limited permissions. The next one is to know some authentication concepts. Now, the flow Kubernetes uses to authenticate a client's request is by firstly having the client present its credentials to the API server. Then the API server uses one of the configured authentication plugins, and then moving on, the identity provider verifies the request information, including the username and the group membership. Finally, the credentials are in order. The API server now moves on to check permissions. Otherwise, it simply returns an HTTP 401 unauthorized client error status report, and with that, the request fails. Kubernetes also supports user impersonation. That is, a user can act as another user. For example, a cluster admin, you could use impersonation to debug any authorization issues. Moving on to the next practice, we have authentication strategies. A couple of authentication strategies are available in Kubernetes, represented by authentication plugins. Depending on the size of the deployment, the target users, and organizational policies, you as a cluster admin can choose static password or token files, or even X.509 certificates, OpenID Connect, Bootstrap tokens, authenticating proxies, and also webhook token authentication. Finally, we move on to the last practice, that is tooling. Now, the majority of the effort in the context of authentication is with the Kubernetes cluster administration. You would start off with the existing infrastructure that you need to integrate with, such as an LDPA server your organization already uses to capture team members and group-related information. You also want to take into account the environment the cluster is, a public cloud provider, a managed service, or an on-premises deployment. The latter is important as you may have different options depending on the environment and may end up having more or less work with the authentication bits based on what authentication strategy you go for. Tools like �KeyCloak, DEX, AWS IAM Authenticator for Kubernetes, Guard. All of these tools really help you with this. So it is a really good practice to work with these tools. Moving on to the next Kubernetes security practices, we have authorization. Now, authorization is assigning permissions to users and applications and in turn enforcing those. Authorization in Kubernetes verifies whether a certain action is allowed by a certain user or application, and if it is allowed, it performs that action or otherwise rejects it and potentially logs the attempt. Firstly, you will have to be aware of some concepts of authorization. Kubernetes authorizes API requests by using the API server, evaluating the request attributes against the policies, and subsequently allowing or denying the request. By default, the permissions are denied unless explicitly allowed by a policy. So I will discuss the authorization flow as we did for the authentication flow. Firstly, the client's request is authenticated. Secondly, if the authentication was successful, the credentials are taken as one input of the authorization module. Thirdly, the second input to the authorization module is a vector containing the request path, resource, verb, and namespace. Finally, if the user or application is permitted to execute a certain action on a certain resource, the request is passed on further to the next component in the chain, the admission controller. Now, if not, the authorization module requests an HTTP 403 forbidden client error status response code, and with that, the request fails. Now that we know how authorization works in principle in Kubernetes, let's look at the ways permissions can be enforced. So we'll be discussing authorization modes. Kubernetes offers multiple ways to enforce permissions, represented by various authorization modes and modules. The first one is node authorization. The second one is attribute-based access control. One is webhook. The next important practice is access control with RBAC. Developed originally at Red Hat in the context of OpenShift, role-based access control was upstreamed to Kubernetes and is stable as of version 1.8 access. You should use RBAC for access control and not use ABAC, or even worse, use none. There are a few parts when dealing with RBAC, like entity, resource, role, and role binding. The actions on a resource that a role uses in its rules are the so-called verbs, such as get, list, create, update, patch, etc. Concerning the roles, we differentiate between two types, cluster-wide and namespace-wide. You will have to figure out what you should use, a role or a cluster role and/or role binding. Now let's move on and discuss some of the tools. Okay, there's several tools that focus on authorization with RBAC. Some of them are Audit to RBAC, RBAC Manager, and Kube to IAM. The next Kubernetes security practices, we have securing your container images. Now I'm discussing things mainly from the point of view of a Kubernetes cluster administrator. Moving on, we will switch gears and focus more on developers, operators, or even DevOps teams who really want to deploy code to run on the cluster. So the software that you run in Kubernetes cluster gets there in the form of container images. The first way is to scan and patch container images. Now, to detect vulnerabilities, you need to use a container image scanner. The basic function of a container image scanner is to inspect the packages included in an image and report on any known vulnerabilities included in those packages. At a minimum, this looks at the packages installed through a package manager like yum or apt packages. Some scanners may also examine files installed at image build time, for example, through ADD, copy, or run operations in a Docker file. Some scanners also report on known malware or the presence of sensitive data like passwords and tokens. Now, to ensure that you're not running vulnerable code in your deployment, you should scan any third-party container images as well as the ones built by your own organization. New vulnerabilities continue to be found in existing software, so it is important to rescan your image on a regular basis. The next one is to patch container images. Once you've identified that you have a container image that includes a package with a vulnerability, you need to update the container to use a fixed version of the package. Please don't be tempted into your running containers and run something like yum update or apt get update, as this is an anti-pattern for containers. It quickly becomes unfeasible to manually patch like this when running hundreds of thousands of instances across a cluster. Factor in the self-healing nature of Kubernetes, which ensures that a failed container will be replaced with a new one, and auto-scaling, which can create and destroy containers automatically, and it becomes clear that it's not really possible to keep up with the patching process manually. The key to patching in a container deployment is to rebuild a new container image and then redeploy the containers based on that new image. The build part is typically automated through a continuous integration pipeline, and this may be executed to cover continuous deployment as well. While CI/CD and GitOps are a part of DevOps, it is worth examining how security tooling fits into the CI/CD pipeline. With this, we reach to the second part, that is CI/CD best practices. Now, image scanning can be integrated in the CI/CD pipeline to automate the process of rejecting images. Many scanners can report a pass or fail for each image, either on basic criteria or more complex custom policies. You can use this fail or pass in several phases in your CI/CD pipeline. That is, a failed scan can result in a failed build, a failed scan before deployment can prevent the image from being deployed, and a failed scan on an image that's already in production can result in an alert so that operators can take remedial action. A good best practice is to use automation to scan all images before they're stored in a container registry, rejecting any images that fail the scan. The next question to consider then is the use of a secure container registry. Several projects aim to help with the problem of ensuring the provenance of the application software running a deployment, like the TUF project. Grapheus is another approach to storing and assuring image metadata. And also the InToto project provides a framework to protect the integrity of the components installed into an image. And finally, we also have commercial security solutions that can add validations that the image being deployed is a precisely approved version that matches your policies. Finally, the last way to secure your container images is by minimizing images to reduce the attack surface. We already discussed the principle of limiting the attack surface, right? There's a general rule that the smaller the image, the smaller the attack surface. Now, by minimizing the amount of code you include in the image, you can definitely reduce the likelihood of a vulnerability. There is rarely a good reason to include an SSH daemon. Also, along these similar lines, other utilities in your images may not be required by the application code. Excluding them will make the running container less useful to an attacker who manages to compromise it. Let me explain this with an example. Suppose that a container has access to database credentials that it accesses by reading from a secrets file. Now, if the container image does not include utilities like CAT or M, it will be much harder for attackers to read the credentials even if they gain access to the running container. Now, if the image doesn't have a shell like sh or bash included in the image, this will make an attack even harder. Taking this idea even further, if your application code can be built as a static binary, you can build an image that contains nothing but that binary. This image will have no utilities that an attacker can take advantage of. As a counterpart, however, consider that by excluding core tooling such as CAT, troubleshooting will also be hard for you, so you want to aim for a sensible trade-off here. Finally, we'll be talking about how to run containers securely. Now that we know how to build container images in a secure manner, we move on to the topic of running those images as containers in Kubernetes. So the first thing that we're going to do is just say no to root. There's little need to run containers at root. There are some exceptions though. If your container needs to modify the host system, for example, modifying the kernel's configuration, you can use it as root. Or if your container needs to bind to privileged ports on the node, then you can be the root. Or even if you're installing software into container at runtime, traditional package management systems might require root to function or store files in a certain location with a different user ID than the user executing the program. Now, if your container does not fall in any of these categories that I just mentioned, principle of least privilege, it would make sense to run it as a non-root user. You can do this by including a user command in the Docker file, defining a user identity that the code should run under. Now let's move on and see how the API server enforces policies. Now, when a client submits a request to the API server and that request has been authenticated and the client is authorized to carry out the operation, There is one more step the API server performs before persisting the resource in etcd, that is admission control. They are included in the API server that you as a cluster admin can configure. The official docs list explains that more than 30 controllers in great detail. Some relevant ones in the context of running containers securely are always pull images, deny escalating execution, pod security policies, node restriction, limit range, and resource quota. Now let's move on and discuss security boundaries and how to release them. By security boundary, we mean a set of controls to prevent process from affecting other processes and or accessing data from other users. From the most outer to the most inner layers of isolation, these boundaries are cluster, node, namespace, pod, and container. Remember that maximizing the defense here requires a joint effort by developers and cluster or namespace admins, since some of the responsibilities fall into the realm of the former and others fall into the realm of the latter. Kubernetes offer two pod level security policy mechanism, allowing you to restrict what processes can do within a pod and how pods are allowed to communicate. So here we have security context and policies. A security context defines privilege and access control settings on either the pod or container level. With this, we have discussed all the Kubernetes security practices. Let's move ahead to the case study, cryptocurrency mining. A famous attack on tested control plane insecurities to allow hackers to use the company's resources to mine cryptocurrency. Additional research shows other approaches that would-be miners are attempting. Ensuring that only trusted images can run in your cluster would prevent, for example, a bad actor with approved access to the cluster from running an expected mining image. Runtime protection can add another layer of defense to ensure that even if an approved image has a vulnerability that allows code to be injected into a running container, that code definitely cannot be executed. Monitoring for unusual activities such as unexpected CPU usage and unexpected resources being scaled out can help your resources are being used by an attacker. With this, we come to the end of today's session on Kubernetes security practices. If you have any queries, feel free to leave them in the comment section below and we'll get back to you as soon as possible. Until next time, thank you.